Hello, everyone. Can you hear me? Yeah. OK, great. So today I'm here to talk to you about the Samsung Shannon Baseband. I must say, this research is not mine. This research is by my friend, Amat Cama. But unfortunately, he couldn't come today. And since he is my friend and I also work on baseband, I decided to do the talk in his place. And Amat is an independent security researcher for his own company, Securin Technology. And he's working on hypervisor and baseband. And he also offers some training and consulting. So if you're interested into getting in touch with Amat, let me know. I can give you his contacts. So today we will talk about baseband, and this is our agenda. We will first cover a little bit the previous work on the modem of cellular phone. And actually, Thomas just did a talk about it. And we will explain a little bit what a cellular network is and what a baseband is. Then we will cover the Samsung baseband called Shannon, how to find bugs. Then we will have a demo. And then conclude. So there are two other presentations. One of them is on this same Samsung baseband, which is by ComSecurus, which is called Breaking Band, and you can find the slides online. And the second one is by KinLab, and you can also find the slides online. So this is an introductory section to explain to you about the technology that composes a cellular network and a baseband stack. So basically, this background is necessary for you to understand the rest of the talk. So what is a cellular network? A cellular network is the network used by mobile communication devices. And by the name, you can tell it's composed by cells. And a cell is basically a land of area covered by a base station which transmits a signal. To form a network, you put together different cells. And in this way, you can cover a large area of country, for example. And when the user transfers from one cell to another, there are some procedure in the network to transparently transfer from cell A to cell B and don't lose your phone call or data connection. So cellular networks are a very complex system. And when you have a very complex system, you need standards and documents describing them. So actually, there are multiple technologies for baseband and cellular network, and different organizations maintaining them. And this kind of organizations are international, and they include several vendors which are involved in this kind of networks, and they publish a standard which you can consult and study. Like I said, there are different technologies, and especially some of them are old, and some of them are more new, and they show the improvement of speed and capacity with time. And you have also different competing technology, because maybe some technology originated in Europe, and another technology originated in the US. So here you can see better what I'm talking about. So actually, in this picture is not shown. This is 2G for GSM, but before we have also first generation of mobile phone, which was mostly analog communication. But now it's shut down basically everywhere. And then second generation was created, and there were mainly two different standards One of them is GSM, and the other one is CDMA1. Then, since mobile network want to improve the efficiency, you have evolution. So you have GPRS and IS95AB, which they are called like a 2.5 generation, because it's basically an improvement over GSM, and they allow you better data speed. Because the trend in the year is that voice call get less and less important, and data packet transmission get more and more important. And you can see the evolution from analog technology up here that just transmit voice, to GSM also, which is channel-based, so it's kind of optimized for this kind of fixed latency voice transmission. But you have a trend switching towards this kind of data-oriented packet communication and higher and higher speed. And nowadays, we can use 4G almost everywhere, and we have LTE. And in the future, soon, we will have a 5G. So I mentioned before that we have documents and specifications. So there are some organizations maintaining these specs. One of them is 3GPP, which is a union of several telecommunication bodies. They maintain specification for this protocol, GSM, GPRS, and LTE. And they provide a detailed, description, of the message and the states and the procedure. So in order to study the baseband, you need to check those documents because they detail the messages and how they are exchanged. So this is a simplified version of GSM, GPRS, and LTE stack. Actually, this is just simplified. It's not really complete. But you can see you have like a more common protocol. You have layers. So you have a physical layer, which we are not very interested into for this talk, because we are looking for memory corruption bugs, and this kind of processing, it's usually not really happening at the baseband traditional code level. Then you have another layer on top of it, which start to get interesting because it might be handled in the ARM code of the Shannon Baseband. And then on top of it, you have the network layer, which is what really interests us. And you can see you have many different components inside this network layer. For example, one for a connection, one mobility management, and another one to manage the radio resources. So what is a baseband? A baseband is basically a standalone component inside your phone which handles the communication with this mobile network. And also it does some very low-level radio signaling processing. So it's usually a CPU with some memory, separate CPU, and some DSP for this kind of signal processing. Otherwise, it would be too slow to do in software. And it must usually support a big number of standards, at least GSM, LTE, UMTS, and potentially also the CDMA ones. As we will see, not all the baseband support this branch of CDMA. So basically, what you need to understand is that your phone can speak to the mobile network only through the baseband. So like all competing technology, you have different manufacturers producing, for example, CPU. So you have also different manufacturers producing baseband. For smartphone, there are not too many of them. And Qualcomm used to be, or maybe still is the leader of the market. and they provide the baseband on the, especially on the top flagship model of a lot of phones, and also Huawei, Samsung, and Intel, and also MediaTek. So we have a baseband here, and then we have a application processor here, and they must communicate somehow because they are two separate CPU. And this communication can happen in several ways. They can use a shared memory, or maybe they can use a USB or some other bus, PCI Express, or whatever your implementation is. So what I want you to understand from this picture is that those two systems, they are totally separate, except for this communication channel. And this last observation gets me to this point, which is if you get a bug on the baseband, if you get code execution inside the baseband, it doesn't mean you can execute on the application processor where your Android or iOS operating system is running. You need another bug to escape from the baseband to the application processor usually. But still, if you run code inside of the baseband, you can do a lot of dangerous stuff, such as intercepting phone calls, SMS, and the internet traffic, and tamper with it. From the baseband to the application processor is very interesting because this kind of IPC, let's say, channel is complex, and maybe it's not very well audited. And there is previous research of this kind of baseband escape. So now we covered the basic and explain the cellular network, the baseband, and some background information. Now we can start to talk about the Samsung baseband. So the Samsung baseband is called Shannon, and it's made by Samsung, of course, and it runs only on Samsung products. And usually they pair it with the Exynos system on chip. But you can also find some USB device with this kind of baseband. And recently, it was popular on non-US Galaxy phones because in US they use often Qualcomm. This baseband is implemented with an ARM Cortex R7 CPU running a real-time operating system. Actually, Thomas in the previous talk briefly covered this concept of real-time operating system and how it works. It has different tasks that communicate with each other. And we will see in the following slides how that works. But to find bugs, I mean, we don't have the source code, of course, because we don't work at Samsung. So we need to get the firmware. But the problem is on the file system, the firmware, it's encrypted. And it seems decrypting it is a little bit troubling. So maybe we can try to grab the firmware at runtime. And luckily, this is possible because it's possible to generate a RAM dump. You can dial this code number, and it opens a hidden application with a system dump menu. So there are several options which are useful for you. The first one is, of course, turn on logging, which you can see here at number 1. And then you can select the log level, which, for example, you can put to high, because it will enable more output and some tracing also. And then you can force a crash on the baseband, and this will generate a RAM dump. And after this RAM dump is done, if you don't have a root on the phone, you cannot access this file. So they include another option on number 4, which is to copy this file to SD card. And from SD card, you can read this crash dump. So I just explained to this. And you can find the dump and the logs inside this folder, and then we can see how can we open this file. This is how it looks when it's doing it. It's actually a little bit funny because it says, do not touch the phone for 10 minutes. And then you have this like debug screen. So our final goal is to take this file and load it into IDAPRO. Unfortunately, it's not like a flat crash dump, which you can just drag and drop into IDAPRO. You need to write a very small loader because there is, on Samsung device, there is a daemon called the CBD, probably some cellular baseband daemon or something like that, which loads the code to loads the code to these addresses, and basically by reversing this binary, you can write a IDA Python loader that takes the RAM dump file and put it back into virtual address representation and load it correctly. So now we have the firmware, and we open it successfully in IDAPRO, but it looks like garbage because we didn't do any reversing. We know it's an ARM Cortex-R7 from the strings, but we don't know anything else. So we know it's a real-time operating system, so the first thing we want to do is to find the task. Because if we find the task, then we are able to find the task for a particular network layer, and then we can find the message handler. So we start reversing from very low level, which is reset exception vector handler. And after quite a while of reversing, which is actually well described in the ComSecurity's talk, we can find a linked list containing the task and their entry point. And this list allows us to identify all the tasks. So now we have a list of tasks and their name. So we need to map the name to the protocol and the component. Actually, this is fairly straightforward because you have like the MM task, which is obviously mobility management. Actually, I showed you this picture earlier. You can see there is mobility management here. So this task will handle message for this component. So we can already start reading the document and trying to find bugs in the mobility management. Then there are others, like, for example, CC, which is call control. And it's actually part of here, but it's not shown. So you can also audit that. And session management, which is also GPRS related. And we will cover this more in detail later. And there are other, like related to LTE, but today we will focus more on GSM and GPRS, actually. So now you have more information to understand this diagram. Basically, if you take this picture, every box will have a task. So if you want to find a bug in GMM, which is GPRS mobility management, you should find the GMM task and start looking for bugs. So how a task works? This is a real-time operating system. So it's, to some extent, more simple than like a Linux operating system. So you have a task entry, and then basically you will have like a while-true loop, which check a mailbox, which is a simpler IPC, or let's say cross-task communication mechanism. If there is a mailbox, a new message, it will process it. Otherwise, it will wait for a new message. And when a task processes a message, it can post a message to another task. So in this way, you can engineer your system into different components, and then maybe some team is responsible for the RR task, and some other team is responsible for the MM task, and they can work independently. So now you have everything you need, actually. You can just pick one task and one protocol box and start finding for bugs. And luckily, the Samsung code has a lot of strings for diagnostic purpose. So it's a little bit of work, but at the end, you can get a good IDB, even without any symbols. So often when you are finding memory corruption, it's also necessary to understand how the heap work. And in this kind of target, the heap is split into 6 pools from 1 to 6. And most of the allocation actually happen from a pool called the main. And it allocates a certain amount of money, amount of memory for it. There are some real-time operating system primitive to allocate memory and free it. And you can see they take a pool number, so you can choose which pool to use. And they have a very useful last two parameter, which is file name and the line number. So you can understand that every time the baseband allocates something, in the IDB you will have the file name. So you can try to understand from the file name why this allocation is done, basically, what they are doing at least a little bit. And then there you have a free primitive, a free function, which takes also a file name. And actually, they don't take a pointer, they take a pointer to a pointer. It's interesting, or maybe funny, I don't know. But they have their heap chunk looks like this. They have canaries, which is AAAA before and after. And when they free it, they check it for integrity. But you see, this is not really a security measure. It's maybe more for debugging or something like that. Like, so, OK, this one maybe too low level. And yeah, let me mention this, actually. Heap has like a bitmap to describe which is free and which is used, and the size and the start and end, usual metadata. So let's show you some bugs, actually. But first, also, we need to set up an environment, because Thomas also mentioned that to do this kind of research, you need to set up like a mobile network, basically. So you need a radio device. We need to basically operate our own small cellular network. And luckily for a researcher, this can be achieved with a small amount of money, with a SDR, which is software-defined radio. And there are some open source projects which implement some cellular network technology. There are a number of SDR available for research. If I can suggest you the more tested one by the community, probably I would pick a Blade RF or a USRP. But there are other alternatives to it. And the Blade RF actually just released the new model. And for software, there are also different options. It depends on what kind of network you want to emulate or you want to operate. So for GSM and GPRS, you have two different technologies which are quite mature. The first one is the 8BTF, which supported the Blade RF quite well. And you can target both the GSM and GPRS. And then there is OpenBTS, which is actually support also a little bit of 3G. They are both kind of easy to compile and run, But I must say, if you use this kind of tool, especially with SDR, you can expect to have some glitches, and they have some problems sometimes. There are other software stacks, especially for LTE. I can recommend you this for SRS LTE. It depends really on what kind of network you want to target. You also need a SIM card, of course. I mean, for GSM and GPRS, you can use a normal one. But if you target 3G or 4G, there is a mutual authentication. So in theory, you should not be able to use like a real carrier device. So you have to buy basically a white SIM card. And if you are concerned of breaking the law, you can also use a Faraday cage, or maybe a very weak signal to don't disturb other communication around. So maybe we have a bug, but how we debug this stuff? Actually, like the other baseband, you cannot really debug it. The only stuff you can rely on, you basically have to do the exploitation blindly. You are already lucky you can get a RAM dump, to be honest. And you can also get a log. So when the Samsung baseband crash, you get a crash dump with the full memory. So you can just write a script to take this dump and extract useful information like register and maybe check some memory. Because, of course, this baseband have no ASLR or something like that. So it's quite easy to write this kind of stuff. So what do we choose to audit? In the scope of this presentation, we choose layer 3, especially NAS, which is non-access stratum, because they have somehow bigger messages and more complex. And these messages, almost all of them, are encoded with an information element, which is there are basically actually 4 types of information element: V value, length value, and type length value, and type length value extended. And we can imagine that maybe in the Samsung baseband they forgot to check those lengths, or this kind of memory corruption can happen. But I should mention there are also other interesting areas which are not information element based. So let's do an example, because maybe this will look a little bit abstract to you. So like I said, our workflow is like this. We have to pick a component. So let's pick a component. Let's pick the call control CC task. And the CC, call control, is part of layer 3 of GSM. And if you open the specification, you can find a number of call control messages sent by the network to the phone. These are the type of message, some of them, which are sent for this particular component, like alerting, which is when someone is calling you and stuff like that. So this is actually a bug reported by ComSecuris. You can see here they have a progress indicator, and the specifications say the length should be 3 bytes, but it's actually encoded in length value. So what happens if the attacker say this is 200 bytes? Well, this bug was reported, was used by ComSecuris in .1 2015, and it was a straight buffer overflow. This is a bug reported by Amat, which I also add, actually. And it's basically the same stuff. You have a cause IE, and it's encoded the same. You have a length value, but this field can be from 3 to 31 bytes. But they don't check for bounds, so you can overflow like 180 80-something bytes on the stack. And there is no stack cookies. So this kind of bugs are trivial, actually, to be honest. Essentially, it's doing like this. You have a TLV, then you read the length from the over-the-air message, and then you just memcopy. So you control the length, and then the buffer is on the stack, so you have like a very straightforward Stack Overflow. So there is another example here in another component, so you can see how things are similar. You just have to pick a task and check the messages and how they are handled. This bug was in location updating accept, and it's a little bit more complex. So it looks like, let me check. It's in the emergency number list parsing. You can see, again, you have a TLV. But the range is fixed, so the baseband have to check it. They have, again, an information element, and yeah, they need to check that this is 50 bytes. Otherwise, they will overflow. But sadly, again, they forgot to check it. So let's check the Amat .1 bug. Amat decided to target a GPRS for mobile .1 because he was scared of bug collisions. And so he started to look into more complex stuff. So he chose GPRS because some part of it are quite complex. And especially he focused on the session management. So this is, you can see the message is quite big. And so he chose this message and start to audit the code. And again, by picking the session management task, we can find the handler for this activate PDP context. And we can find where those messages are processed. I know you cannot see this code, but you can see it looks slightly complex. So there is a good possibility to find bugs, hopefully. So PDP actually stands for Packet Data Protocol. Sorry, I have to go a little bit faster. And basically, it encodes option for protocol data. And it includes additional information. So the baseband must parse all this stuff, and must do it correctly, of course. And one of these supported protocol is IPCP, which is Internet Protocol, of course. And there is the problem is they check the length here, but they simply do nothing about it. Maybe they forgot something, but anyway, then you have a for loop with a controlled length. And you can see the buffer on the stack is on the stack, and it's of fixed size. So this one, again, is a straight buffer overflow, stack buffer overflow. The problem is you cannot send this message directly, because Thomas also mentioned in his talk, there is a state machine problem here. If you send this message directly, the phone will simply ignore. So it's not so easy. We have to trick the phone into the right state before sending this message. And to do that, we can send before another message, which is request PDP context activation. The phone will reply with a PDP context, activate PDP context request, and then we can send a PDP context accept and trigger the bug finally. So we need to do ROP and then switch to shellcode. And then there is the same problem that we had at .1 with KinLab, which is how to demo the code execution on the baseband, because we don't have the screen. The baseband is separate. And Amat chose to write a file into the Android device by using the remote file system API, because the baseband have to store some persistent information somewhere, and they don't have a disk to do it. So they must send some message to the phone to the AP to do that. It can be on the file system, or it can be on the NVRAM, or depending on the vendor. Or maybe in the meanwhile that the demo is ready. Like I mentioned, you don't have debugging capabilities, but you can write your own hacked debugger. Since you have a remote code execution bug, you can just insert a breakpoint, let's say. And then you can also add some tracing. And after you collect those traces, you can save them in the remote file system and just read them with ADB. So to conclude, I hope we show you that baseband exploitation is not as hard as it seems. You just need to get into it. And you don't even need to know too much about the network in order to exploit them. And they are a complex beast, so there might be a lot of bugs waiting to be discovered. And there are many targets out there. So if we have the demo, otherwise I will take questions if you have any.